So let's jump right back in here. Let me show you what I got going on today. So what you can do with this HHO gas is you can take a piece of tungsten and melt it right into the center of a rock. You can melt copper, stainless steel. You can stack rocks together just like this, and you can't fit a human hair in between those welds. They're watertight. So a lot of people have asked me, how did the Egyptians manipulate those stones and cut them where they're like butter? Well, HHO gas is the answer. Now these are lava rocks and they manipulate very easily. They turn into glass. And I gotta look through the camera to do this because it's so bright. See, I can turn these rocks directly into like a gel. So think about that. So it's different than anything you've ever learned. Working with this gas does a lot of different things. You can do woodwork, working with stones. I mean, I can stack this all the way up to the ceiling if I want to. So the hydrogen atom, it's like a miniature time clock. Think about this. It acts like a miniature universe. You have its electrons spinning around that proton. In the electrolysis process, it loses that electron. It becomes positively charged, and it's attracted to the negative electrode. Think about that. I want to talk about stability here in this video and what's going on with these atoms, these gas atoms, once you break them apart. Once you have your oxygen and your hydrogen atoms, you got to think about what's happened to them once you've broken them apart. Okay, they want to remain in a stable state of equilibrium. The stability of atoms is a very key important part. It determines whether they're radioactive or not and how long their half-lives are, or whether if it's an isotope or not. So you have to remember that. The more you push an atom out of a stable state of equilibrium, the more neutrons you add or remove to one of these atoms, the more unstable it becomes. You wind back its clock. Think about that. Once you destabilize an atom, you can't just fix it immediately. You have to wait until it slowly comes back into stability. That's what the half-life is. Think about uranium. It's radioactive for billions of years. So it takes a really long time for that to get back to normal. Your entire lifetime. So it's very important. So you push an atom out of its equilibrium, it becomes radioactive, and that's not happening when you do electrolysis. When you're working with electrolysis, you're only working with the electron. You don't mess with the nucleus of the atom. You're not changing the stability or anything, and that's where these nuclear power plants have gone wrong. All this radioactive waste that they're getting from these power plants. That's just something I wanted to point out. Some of these things are radioactive just for a few seconds or a few minutes, and then they turn right back to a stable state. But some of them, it could take a billion years. So it's very important to remember that. The electrolysis process is important to understand. We've gotten rid of the neutron. We're not using that anymore to make electrical power. It's gone. That's what's caused all the problems, and who determines who has the right to make an atom unstable, Because once you do it, you can't switch it back. Don't forget this. If you use your goggles, if you ever go welding these rocks together like this, it's very bright. This is how I did it, so you can get really close up in there and just weld them together. It's pretty amazing, huh? But the electron, that's what's important. Think about that, the electron. 21st century fire. In the electrolysis process, we're not making any changes to the nucleus. That's what's important here. The hydrogen, the oxygen atoms, so there is no radioactivity. But the atoms are in a very reactive state. That's from gaining and losing electrons. So they're highly reactive. what's cool is you can change the molecular state of other atoms, of other solid materials. Think about that. Turn that into glass. So take a look here in my book. It says radiation, energy released as particles and waves. It is frequently used to describe the weak nuclear force that causes the nuclear decay of unstable elements, radioactivity. So that's exactly what's going on here with this uranium glass. I'm going to put my Geiger counter on here. We'll give that a second to get going. And if you look at the heavier elements here, they're labeled with the trifoil symbol. They show you that they're radioactive. All these higher, heavier elements, especially the man-made stuff. All this everything after plutonium is man-made. It just keeps going. See, and that was the problem with the nuclear industry, was the neutron. See, and in a hydrogen society, you're going to get away from all that. You know, using the water molecule, using water that we drink every day. That's the way we're going to get away from that. See, this uranium is just another non-renewable resource. You know, it's helped the big wheels, but it's created all that waste. But that has a lot to do with why atoms are radioactive, because they're very unstable, you know. Think about it, uranium atom is throwing off alpha particles, and it's throwing off beta particles, so it's throwing off electrons. That thing's throwing off electrons, literally. And one day it will go back to a stable state. It will take it a very long time, billions of years, but it will go back to, it'll turn into lead one day. It'll go all the way back down this chart, and it'll turn into lead. So you're getting away from the neutron, that's the key. That was the fault of the nuclear industry. That was the big deal with that, you know, using neutrons to make electrical power, splitting uranium atoms was a very bad idea. It's created tons of nuclear waste, and it's just wrong. So you're not going to get that in a hydrogen society. So here's some different stones right here, and they all act different depending on if it's rose granite, quartz. They all have different hardness on the Mohs scale. There's a scale that goes from 1 to 10. Quartz is like an 8 or a 9. It's really hard. I think rose granite's one of the hardest stones that there is. Let me light this flame. What we're going to do here, let me show you this. I thought this was important. Pictograms. I've showed you guys a lot of those. Symbols and pictures that are etched in stone. And, right underneath it, piezoelectric. The ability to carry electrical charges, as in the case of a quartz and human cell membranes. So that's pretty cool. Over here on this side, quartz crystals, tools for detecting frequencies because they are hexagonal and excellent receptors, and they are piezoelectric. Got a quartz crystal setting right here. I'm going to show you what it does when you hit it with the flame. So I'm going to hit all these with different flame, but I'm going to put my goggles on. Give me a second. Alright, so I'm going to show you that every stone acts different when it comes in contact with this flame. So you never know what they're going to do. They could shatter, they could fly apart. Let's see what this one does. I've never checked any of these stones. These are right out of the driveway, some of them. Wow, it just turns into a dust. Look at it. It kind of exploded, and it cut it flat too. Let's try the next one. What's this stone gonna do? It just glows and stays together, no damage. Interesting. Try the next one. Oh wow, this one just explodes as soon as you hit it. I don't like this one. it shatters and the rocks go everywhere. Let's try this one. Same with this one. Yeah, it kind of turns white and falls apart. Let's try the next one. Oh wow, this one just flakes off. Gives off a good candle-luminescent reaction. Oh wow, it just exploded. Holy cow. Let me go to the next one. Oh wow, I can tell already this one's gonna fall apart as soon as you touch it. This one just flakes off into thousands of little pieces. So they all act different. They all act different. I already know what the quartz is gonna do. It chips off. It chips off really fast. Goes every direction. And you know how hard quartz is. Look at that. Look how easy you could tear up a quartz. Okay, so the strong nuclear force, the force that binds quarks which make protons and neutrons. It's the nucleus of these atoms that we were talking about earlier. So the nucleus is very important. And you want to mess with the nucleus. That's how radioactivity is created, using neutron sources and things like that. So you want to stay away from that. And that was the whole idea of switching over to a hydrogen society. You're just working with electrons and protons. It's very important. The nuclear strong force is what holds together those protons. So think about that. It makes you wonder, you know, if you think about this, electricity, water, rocks, you know, these are some of the most abundant things on planet Earth. So it makes sense that they use this stuff to help build the pyramids. I mean, it's just a suggestion. Because nobody really knows. If anybody ever tells you they know how the pyramids were built, they're lying to you. Because no one knows. That's the mystery. But look at what I was able to do to these hard stones just fooling around. You know, some stones I could melt it and turn it into glass. And shove a tungsten rod right through the middle of it. You know, some rocks I was able to weld them together, stand them on top of each other, like Yoda. You know, crystals, one of the hardest things in the world. I could cut it like it was butter. Some rocks melted. Some I was able to cut them completely flat. Look at that. Think about that. That's a hard-ass rock. I was able to cut that flat with that flame. I mean, with a little practice, imagine what I could do. You know, some rocks completely exploded and fell apart. I didn't like burning that rock. It went everywhere. It's in my hair and everywhere. You know, some rocks, it made it easy for them to come apart. It seemed like it strengthened this one. That's the power of that flame.